I'll just go over all the answers because this was a low scoring quiz. I mean, some of you got 5, which means you got a 0 really on the quiz because I'm taking off only -1 for the wrong answer. So I want to go through the quiz. So when you are trying to find out the third normal form decomposition, so the first thing is you find the key. So for the first relation, you have A going to B and C going to B. So you never have A or C on the left-hand side. So, I mean, you never have A or C on the right-hand side of a functional dependency. So out here, it's rather easy to check. You put A, and C on the left-hand side. You can generate all 3. So the key is AC. So when the key is AC, you can start looking at the options. So the very first option, R1, goes to ABC. It's very easy to eliminate this because in R1 is equal to ABC, you have 2 functional dependencies, A going to B and C going to B. And in both cases, I can't underline because at least AC, so the key is AC. Yeah, so in both cases, you have the left-hand side is not the key and B is a non-prime attribute. So you can say, okay, it can't be the first option. So let's look at the second option. So in the second option, you have 2 tables, R1 and R2. And for R1, you have A and B. So in this case, you know that A is the key. Anyway, from the functional dependency, A goes to B. And then you're bringing over A to the other table, R2, and you have RC, A and C. So this one is the correct answer. So you don't have to go any further since you're supposed to select only one option. So you can stop there. But let's just go down and check the rest of the tables. So in this next table, you have this table R1 and R2, but there is nothing that connects the 2 tables. So you cannot get the original table back from these 2 tables because there's no intersecting attribute. And the third one, and the same thing with the D, so this can't be either. And so if you look at option D, you have AB and BC with the intersection being B between the 2 tables. But out here, you're not going to get the original table back either because you always, the attribute that intersects 2 tables has to always be a key on one of the tables. And that's not the case out here. So you're not able to bring the original table back. So, so the only option that is correct out here is option B. And actually, for this particular table, there are actually, for this particular problem, there are 2 tables. There are 2 different decompositions that would be fine. So another possibility that would have been correct would have been you could bring R1 is equal to CB and then R2 being AC. So here you're starting with the functional dependency, C going to B. In this one, we started with A going to B. So that's how you get the answer for the first problem. Does anyone have any questions? So for the second problem, we have 2 functional dependencies, A going to BC and B going to A. So again, you have to find the key. So if you look out here, you have B and C are there on the right-hand side, and we have A on the right-hand side too. So D is never appearing on the right side anywhere. So therefore, D has to be in the key. So you have to start up with D. But if from D, you cannot generate the rest of the attributes. So let's look at AD. So if you look at AD plus, you will get AD, but A gives you B and C. So AD is a key. Similarly, let's just look at AB, because we have that attribute B goes to A. So we'll get A, oh, sorry, what did I do? D, it should be DB. So we have, A, so bring D, B, and then B goes to A, and then A goes to C. So you can get, so the two keys for this are AD and BD. Okay, so so let's start with the first one option, which is ABD and AC. So in this case, the attribute, I mean, if you look at the functional dependency, you have A going to C. So that's how you get the stable AC. And then you're bringing A over to this, to R1. So that's how, so A is the thing that connects these two tables. So then you have this table ABD. And for ABD, of course, the key is either it's going to be BD is the key, or the key could be AD. So it could be both keys. So actually I should, so so the key for R1 is either it's AD or it's BD. Okay, but you do have one functional dependency, which is A goes to B and B goes to A. So we have this functional dependency out here. It's kind of messy, but you have the functional dependency A goes to B and B goes to A. But this functional dependency, remember that A and B are both prime attributes. So even though we have this functional dependency out here, because the right-hand side in either one is a prime attribute, it's okay. You can leave R1 the way it is. So therefore, this first option is correct. This table is in, this decomposition is in third normal form. So this one's correct. Similarly, if you go down to the next one, R2, where you have B going to C. So here again, you're starting with B goes to C. And that's okay, because remember, B goes to A and A goes to C. Therefore, from the transitive property, B goes to C. So B is the connecting attribute between these two tables. So, and B is the key for R2. And then again, R1, for the same reason as earlier, R1 is in third normal form. So this option is also correct. So that, therefore, the answer to this problem is that both the above decompositions are correct. Okay, so then let's look at the next one. Which of the following, again, it's the same. So I'm looking at the same relation R. And so now we're looking at ABC and AD. So, so again, out here, you're looking starting from R1. If you look out here, the attribute that's connecting both the tables is this one. Okay, and so here it's the right-hand side. We are looking at something that is saying A goes to BC. And you're connecting with A. So again, and so so A is the connecting. A is a key in R1. So R, you can get R from R1 join R2. So the first option is in third normal form. So this is correct. So again, let's look at the second option. It's the same thing. The second option we have. So in the second one, what we are, the connecting is B. So what you're looking at is B goes to AC. So therefore, again, for the same reasoning, here again you get, so that's the answer, both of these. So actually all 4 of the decompositions are correct. So does anyone have any question on this? So let's look at the next problem. We have we're given all of these functional dependencies, and you have to find out which of these are correct. So again, you have to start with the key. So now let's look at all the attributes that are, so which are not, so you have A is appearing on the right, C appears on the right, D appears on the right. So if you look at the relation R, the 2 attributes that never appear on the right-hand side of a functional dependency are B and E. So let's start with B and E and see, is B and E a key? Okay, so because the key will have a minimum of B and E because neither one appears on the right. So you know for sure that B and E have to be in the key. So I just want to see, are they sufficient? Okay, so we have B and we have E. So, and then we have this E goes to CD, so we can bring that down here. So we have C and D. And then we have that, I mean, either we can look at D going to AC or we can look at CE going to A, so we can bring A down, which means that BE is a key. So in this case, since I'm asking you to mark only one correct option, there's only, I mean, you can just go down here and see BE is the key. So therefore this has to be correct. So that's all you have to do and you're done with this problem actually. The moment you get one right option, you don't even have to look at anything else. But since I'm going over the quiz, I'm going to just look over all the rest and see, okay, are any of the others correct? So let's look at A, C, and B. So let's see, from A, C, can we generate B? From AC, you can't generate B or anything else for that matter. So let's look at the next one, ACD. That's it. You can't get anything beyond that. And let's look at C. Again, C can generate nothing else. So, I mean, the other 3 options are pretty simply, you can just wipe out and say that none of them really work at all. So really only the last option was correct. Okay, so now again, so now we know the key is BE, and we have to find which of the following relations would be produced by the 3NF decomposition algorithm. So select one. So, so let's start with the first one. And from the first one, we can immediately say that it is not in third normal form, because I mean, anyone, you can look at D goes to A and C, but D is not key. And A, C are non-prime attributes. So that's not a normal form. So let's look at the next one, ABC and BDE. Okay, just look at the table R2, BDE on this table. So for BDE, the key for R2 is BE. So BE is the, oh no, actually, yeah, BE is the key for this table because, you know, you can't generate B from anything else, but you are given this functional dependency, E goes to D. So we have this functional dependency, E goes to D. So in this case, E is not key. So, and neither is, and okay, so here, let me just see, E is not key and D is a non-prime attribute. Therefore, this table R2 is not in 3NF. So therefore, this option is incorrect. So you can just get that out. Similarly, the next one is the same reason, because you still have this table BDE being, and again, is not an R2, but again, if you look at the connecting thing out here, the thing that connects these two is the attribute D. So you're also going to get that R is not equal to R1 cross R2. So, even from that viewpoint, it won't work out. I'm trying to see on this case, would it work out either? Yeah. Same here. You can also, even if you didn't catch the fact that R2 is not in third normal form, you won't get the original table back by the joining of these two tables, because the attribute that connects the two tables is not a key in either one. So let's look at the last one. So in the last table, since you have one correct option, you could have just marked the last one, but let's look at the last one and see why it's in third normal form. So we have R1. So let's see, which one would we start with? Let's pick up table E goes to D. Okay, so let's start with this one. So we have R2, where you have R2, which is the functional dependency E goes to D. So we have E goes to D. So that would leave you with the table. So once you pull that functional dependency out, you have a table A, B, C, and E. Okay, so you have the table R dash is equal to A, B, C, E. So from here, we also have, I'm trying to see, how do you get, so you have, I think that's not the way to start with this one. Let me just start. I don't think that's the right way to start with this one. I think we should start with R1 actually. So I started wrong because I can't get any of the other tables otherwise. So you can see that I started wrong on this one, because you couldn't get R1 and R3. So let's start with R1. I think that's the right place to start. So from R1, we are getting that D goes to AC. So we have D goes to AC. So you have A, C, and D out here. And is there any other key in here? So we have C goes to A, E goes to CD. So there's nothing else. So R1 is in third normal form. So the remaining table, R dash, will be A, B, C, D, and E. So R dash is going to be B, D, and E. But in B, D, and E, the key is B and E, but you have this functional dependency of E going to D. So you got to pull that out. So you're going to get, so R dash is not in third normal form. So you have to further divide it. So you're going to get R. So in this case, I call it R3. That is going to, what is it, R2? R2 is going to DE, where the key is E. And then you have the remaining table. R3 is going to B and E, where both are keys. So that's how you get the third one. So the last option is the only one that is correct in this one. So does anyone have any questions? Okay, I know I spent a lot of time on this, but it was a low scoring quiz, and there were a few people who actually got 5 or a 6, which means they got either all wrong or just one correct. So I really did want to make sure that you understand how to do these problems. They are actually rather tricky because I was looking at the quiz and there were people who were finishing the quiz in 4 minutes and 5 minutes. It was way too short. I mean, that means you're going through a question way too fast. So they look very easy, but they're not. Then there are more tricky, or it at least requires more than maybe 30 seconds. If you have more time, just spend a little more time on it. Anything else on the quiz? Okay, so then I would like to move on to the fourth normal form. So we've done the third normal form and we've done Boyce-Codd normal form. And if you've looked at I looked at the assignment, I have a few questions on second normal form in there because I do want you to take a look at second normal form. So the next thing I want to look at is the fourth normal form. So far we were talking about functional dependencies, but fourth normal form really is based on multi-value dependencies. Dependency. Okay, so it's based on multi-value dependency. So the thing with fourth normal form is that it is much stronger than the previous normal forms that we did. So if your table is in fourth normal form, then it is in Boyce-Codd normal form, and which means it's in all the normal forms also that are below that. So before talking about fourth normal form, I want to explain what multi-value dependency is. So I'm going to have to use some small example to explain it. So let's say we have this table, employee table, which has 3 attributes: name of the employee, the project the employee is working on, and the employee's dependents. And so this table has all the 3 attributes are key. So this table has the following data. So let me just write down. So we have John. So there are 3 employees, John. John works on projects X and Y. And project Y. And John has dependents. Mary, Sally. So John works on 2 projects and he has 2 dependents, Mary and Sally. Okay, and then we have Bob. And Bob works on project X. So he works on only one project X. And he has dependents. Jill, Jake, and Mary. So he has 3 dependents. And then finally we have Sue. And she works on projects X, Y, and Z. And she has dependents. And Tim. Okay, so this is the data that we have, and they're all in this particular table. So let me just put it down as a table. So I'm going to go over MVDs. MVDs are actually a bit confusing. So it is worth the time that I'm going to spend making the small table, because if you don't understand MVDs, you don't get fourth normal forms. So you really have to understand MVDs. So we have these this table. So I'm going to write down the table. So we are E name, P name, and dependent. Let me just move it to the, okay. And so we have John, and he works on project X, and he has dependents, Mary and Sally X, John. But he also works on project Y. And that doesn't change his dependents. His dependents are still Mary and Sally. So that's John. Okay, so the next person is Bob. So we have Bob. Bob works on project X, so it's simpler. He just works on one project, but he has three dependents, Jill, Jake, and Mary. And then finally we have Sue, who works now. So Sue is a bit of a pain because she works on so many projects. So we have to, get her onto all of these. So we have Sue who works on, oh, it's a pain, X. And okay, so now you can see this table. And as you can see, it is, a bit, there's a lot of redundancy in this table. In the sense that you have to keep repeating, but the problem is, how do you divide this table? Because, you cannot say that there is no functional dependency in this table. So that's because if you look out here, we have John. So let's look at John, for example. So we have John. And John, for the one value of John, we have two values of project name. So we have both X and we have Y. And similarly, for one value of John, you have two values of dependents. You have both Mary and you have Sally. So John is not functionally dependent on either p name or dependent. And anyway, you look at any of the attributes out here, there's no dependency in this table. But the problem is that there is something. It's not functional dependency, but there is a connection, because out here we have X, but you also have that, if you have Mary and Sally out here, you know that you have to have Mary and Sally out here. If someone forgets to add Sally to the, with a data entry mistake you make, and you add John project Y, but you don't add Sally, there is a mistake in the table. And you would like this mistake, to somehow get caught if you is there, because it's a fundamental data entry mistake. So the question is, so this is what really is multi-value dependency. This is not a functional dependency, it is a multi-value dependency. So out here, what you say is that, so this is called, so what you say is that ename multi-value determinant. So this is, um, it's shown with a double arrow. So where earlier functional dependency, we do only one arrow. For multi-value dependency, you do double arrow. So what you say out here is that ename multi-value determines pname, and same time ename also multi-value determines dependent. Or in short, you could write this down as, the two things, you could have combined it together and written it down as multi-value determines let me just move this. Because it multi-value, when it multi-value determines p name, it's also actually multi-value determining dependence. So it's multi-value determining both. So so when you have this kind of multi-value dependency, it's not good to have one table, because it's very, there's just a lot of redundancy. There is the possibility of having errors. So when you have something like this, it's you say that this table employee with ename so this table is not in fourth normal form. So you should divide it into a fourth normal form table. And so when you have a table like this, you should divide it into the two tables. So you should divide it into R1, which is ename, pname, and the key is ename, pname, and then you have R2. You would do has ename dependent, and the original table R, which is emp, you can bring it back as, so we can get it back from the join of R1 and R2. And R1 and R2 are in fourth normal form. So, so do you think you kind of understand, at least get the basic idea of MVDs?
Okay. Aren't these also called lookup tables?
Lookup tables. I actually have never heard that from, did you see that somewhere? Okay.
Yeah, I've had it explained to me as that before.
Oh, and it's what is called lookup tables?
Yeah, because you're mapping the name to possibly a bunch of p names or possibly a bunch of dependents in separate tables. So like if you need p name information, you're just looking it up from a table that maps those.
Oh, okay. I actually never heard lookup. So you may be correct, actually. So out in database, I think they just called, multi-value dependencies. So, but if you've seen it before, then it's good. So it'll be easier for you to understand, because MVDs are a tad bit confusing. So let's look at some, I'm going to do a few examples before I move on to the fourth normal form. So let's look at of MVDs. I just want to make sure you get MVDs before we go further. So let's say we have this table where we have again, ABC has the following values. It has A1, B1, and C1. And suppose you're given that A multi-value determines B. And so you're also given A1 and B2. So, but you don't know the value of the C1. But if you're given the information that A multi-value determines B, you know that you should have a C1 out here, because A multi-value determines B. So therefore, when A1 goes to B2, so you must have a C1 out there, because A multi-value determines B. Okay, so let's look at a slightly, the same example, but different, more values in the table. So we have A, B, and C, and we have So now we have A1, B1, C2, and then we have A1 and B2. So if you're given that A multi-value determines B, and even if you don't have the rest of the data, but you have this information that A multi-value determines B, then you know that the following information has to be filled in. So you have to enter the following information. If you're given this information, A multi-value determines B. So, okay, so I would also like you to take a look and see. So we are given A multi-value determines B. So my question is, does A multi-value determine C? So what do you think? Does A multi-value determine C? So, I mean, actually for this one, you can look at the data and you can see that yes, because when A1, C1 goes to B1 and B2, so we have A1 goes to C1, and then for C1, it goes to B1 and B2. And if A1, when A1 goes to C2, it also goes to B1 and B2. So yes, but I just want to say that this is called a trivial MVD. If you have a table with, in this case, we have a table with 3 attributes. If A multi-value determines B, then A will multi-value determine C. So there is so if you're given a question like this, you don't have to go through all the entire data. It is a rule. If A multi-value determines B, then A will multi-value determine C. And if you have a table with 4 attributes, A, B, C, and D, and if A multi-value determines B, then A will multi-value determine C, D. So all the remaining attributes. So that's a rule. I'll write down these rules later. I just want you to know this. So let's take a look at another example. So again, we have this table R with, I'll pick a small table, A, B, and C. So we have, so let me put in the following values. We have 100, 30, 200, 323, and 321. So we have 132, 122, 123. You have to be really careful with the values you enter in here. Okay, so this is the table that you're given. So I want to ask you to look at the following. So my question is, does B multi-value determine A? So I want you to look at this and answer this question. Does B multi-value determine A? So 30, when you have the value 30, it's kind of trivial. So look at the value 20 for B. So if you look out here, the answer to this, as you can see, is no, because you have a 1, so you need to add out here a 2, and out here you need to add a 1, because the thing with multi-value dependency is that if 20 connects to 100, then all the other, so it's like you can think of 100 has John. If John has works in projects 100 and 300 and he has 3 dependents, then you have to show the 3 dependents in the other case too. So out here we don't have that. So does B multi-value determine A? The answer is no. And if B, and so like I mentioned earlier, once you know that D does not multi-value determine A, so you don't even have to look for C, because the answer to that will also be no. If it does not multi-value determine A, it is not going to multi-value determine C either. So does anyone have any question on this part?
Professor,
Yes.
so what about B30? Consider if it is satisfying with 20, but what happens? I mean, how can we check for 30?
You don't have to check, right? If all you have to find is one instance where it does not satisfy. That's all, because that's what we use. If to find that something satisfies, you have to check all the cases. To find that
Okay.
something does not satisfy, all you need to find is one counter example, one case. So you stop
Yeah.
the moment you find one case. So
So
30, I mean, when you look at 30, you can't do anything. Because 30, there's only one value. It's like saying that John works in project X and has a dependent Mary. So I mean, there you can't look at 30 for anything. So you have to look at 20. That's why I said you need to start at something where it has more than one value, more than one
okay.
row. Yes. So remember, proving is a lot harder than disproving. Disproving needs only one counter example. So B does not do for A, and if it doesn't do for A, it will not do for C. There's a rule, so we don't even have to look. But let's look at, does C multi-value? So I want you to look for the next one. Does C multi-value determine, should we look at B, or it doesn't matter? B, and if you look for either one, C multi-value determine B. If it does not, if it multi-value determines B, it'll also multi-value determine A. So you don't have to look at either one if it does for one. So please look at this one. You can look up either C going to B or C going to A. It doesn't matter. Okay, because so in the case of C going to B, like I've shown out here, because it does determine, you have to look through all the cases, because if you find even one case, one counterexample, that then it disproves. So proving is harder because you have to look at all the entire table to prove that one attribute multi-value determines another one. So in this case, we have a tiny table, and yes, C does multi-value determine B, in which case it also multi-value determines A. So is there anyone, did you get this? And let's just, since we are going through this, let's look at the third case, which is, which one did we miss out? C, B. So let's look at A. So the next one is, does A multi-value determine B? And the same thing, if you can look at A multi-value determine C, either one's fine. So the question is, does A multi-value determine B? So you can see out here too, because all you have to do is find one counterexample. So if A does not, which will imply that A does not multi-value determine C either. So the answer to that is also no. Okay, so I hope you understood this example. Okay, so I'm going to give you a slightly larger example. So you can take a look at the next one. So I'm going to look at 4 attributes. So far, we are looking only at 3 attributes. So let's look at 4 attributes. Trying to X 1, 20, 100, Y. To be careful when it's because you mess up even one value, it messes up the whole thing. 10, 100, Y. I guess that's 1. I'm going to put a different color for 2. 2, 10, 200, X, 2, 30, 300, X, 2, 30, 200, X, 2, 10, 300, X. Okay, so that's the table. So it's almost 10 o'clock. So I'll continue with this example in next class. So I wanted to ask you whether, let's say, just we can look at this and see, does A multi-value determine B? Does A multi-value determine C? D? Does A multi-value determine CD? Or B multi-value? So we can look at different cases. But I mean, we'll look at it. So I mean, if you do get a chance to, you could look at A, does A multi-value determine B? So you can look at that. So I'm going to continue with MVDs in the next class. Does anyone have any questions or something?